talk about friction force. We really have two different types of friction forces depending on if the object is moving or not. If it's not moving, it's a static friction force. If it is moving, it's a kinetic friction force. And static friction force is always greater than kinetic friction force. In other words, it takes more force to get an object moving than it does to keep an object moving. And so static friction force exerted on one surface by the other when there's no relative motion, and it's what keeps an object from moving. An object only moves when the force exceeds the static kinetic friction force. And a lot of times the diagrams for the static friction force and the kinetic friction force look very similar to one another. So let me talk about kinetic. Kinetic is when force exerted on one surface by the other when the surfaces are in relative motion, and it causes a moving object to stop. So the model we're going to use for friction problems, friction depends only on the surfaces in contact. And so the force of friction, if we have a kinetic friction force, we can say that's equal to mu of k times Fn, where Fn is the normal force. Mu of k is a proportionality constant, which we call the kinetic coefficient of friction. And that's a relationship between the two surfaces that a lot of times you can look up, or in most of our problems you have to solve for those. So forces involve magnitude only because force of friction and Fn are at right angles. If we have a static friction force, we can say that 0 is less than equal to the force of static friction, which is less than equal to mu of s times Fn. So mu of s times Fn is going to be the maximum static friction force that you can have before the object starts moving. So let's take an example here. If we have, let's say, a box sitting on a table. Let's draw the forces on the box. We've got mg acting down. We have Fn acting up. And let's say that we're pushing the force. So we've got some sort of a push force, I'm going to call it Fp. And then what opposes that is FFR. Now, it doesn't matter if it's moving or it's sitting still. This is all going to look exactly the same. So it doesn't matter if we're talking about kinetic friction or static friction. And so let's sum these forces up. We now have forces acting in two dimensions. So what we can do is say the sum of the forces is equal to ma. And let's just say, for the sake of argument, this is static friction, it's not moving. So that ma is going to be actually equal to 0. And so we can sum the forces up in the x. So I'm going to say sum of the forces in the x is equal to ma. So in the x direction, we have two forces. We have Fp, I'm going to make that positive, minus FFR. If it's just sitting there, it's not accelerating, that's all equal to 0. In the y direction, we have Fn minus mg is all equal to 0. And it can't be accelerating in the y direction because it's sitting on a table. It can't really go up or go down. So we know this about FFR. We just said it here. Force of friction is equal to mu of k times Fn. Well, what's Fn equal to? We can look down here and say that because of this equation, Fn is equal to mg. And so we can then take this and plug this into here. And so we get FFR is equal to mu of k times mg. And then we can plug that into here and say Fp minus mu of k times mg is all equal to 0. Now let's say that this is a, I should have called this mu of s, I'm sorry, I messed it up. It's mu of s because I said originally it's not moving. Now let's say that it is moving. And so now what we can give it an acceleration, or we can say it's moving at a constant speed. We'll go ahead and give it an acceleration. And so what that's going to change here is this. That's going to make this equal to ma. There's still no acceleration in the y direction, so we're just going to leave that equal to 0. So that makes this equal to ma, and really all it changes is this becomes mu of k, this becomes mu of k. And so that's how you solve friction problems. That's at least a start anyways.